Can you guys see my screen?
Yep.
All right, so today's lesson again is on the same website. So if you go to the EVolocity website for this module, it's any@evelocity.github.io. I'll post that link here just in case. Copy. Not pasting. Right, and in here we have the lectures, which we're going to go through the 2020 build workshop notes. And the Proteus file for today's is under examples, Arduino module 3. So if you click on this one, download the module 3 file, then open it up, put it onto your desktop or something, and double click to open it, you would get this Proteus module that I have created for today's lesson.
Okay, it's downloading.
Okay, I'll give you a few minutes. How are you going, Les? Did you download it?
I'm just doing it now. I haven't done it. Should be reasonably quickly.
Are we all good? So next we're going to go to lectures tab and click on the lecture notes for today so we can look at some of the theory behind what we're going to do today. So if you skip through, so it has all the lectures for all the modules. So if you go to slide 37, so we are going to talk about today tachometers and temperature sensors. So tachometer is used to measure the speed of your cart. The temperature sensor, we can use it to measure temperature of different devices. In this case, one of the critical things that you should aim to measure, especially if you're using a lithium battery, is the temperature of the battery. So we'll assume that you're going to use the temperature sensor to measure the battery temperature, and the tachometer, we're going to use it to measure the speed of the cart, as well as we'll extend this analysis later on to see whether we can use the tachometer not only to measure the speed, but also the distance you travel, the acceleration of your cart, and get quite nice data about your cart so you can improve the performance as you go.
Yeah.
Right, so to measure the speed of the vehicle, there are a number of ways you can do. And one of the ways that you might probably think about is using GPS. You know that if you have a GPS, you have a phone that has GPS, any device that has GPS, you can download apps and you can look at the speed on the phone if you do that. So that's one way to do it. It's accurate as long as you have good visibility in terms of not much cloud coverage. You're not covered in those areas. This will give you a nice accurate indication of the speed, acceleration, the distance traveled, and so on. Also, in case you want to build your own thing, there are modules that you can buy and plug with the Arduino so that GPS modules, they would tell you the distance traveled. This tends to be a bit expensive, and there are simpler ways to do. So we are looking at the simpler way to do this, which is using something called a tachometer. A tachometer basically counts how many rotations this wheel do every minute, or what is its angular speed in radians per second. Do you learn angular speed at high school?
No.
In year 13, they do.
I see.
What year are you guys at Glendale?
So it's like year 12, but we are kind of new.
Uh-huh.
It
Okay.
probably won't happen till next year. It's a year 13 topic.
I see.
Oh, I see.
So basically, the tachometer, what it does is it basically counts how many times this wheel rotates, if you want to think about it, per minute. Okay, and
Okay.
that we can relate to the speed the wheel is rotating. Because it's a wheel, it's rotating in a circle. We call it the angular speed or the rotational speed, not this a normal speed that if you're running. Then the speed that you're running is in a straight line, and we call it the linear speed. Whereas in this case, we call it the rotational speed of the wheel, because it's spinning around rather than just going from one place to another place, right?
Can it be attached to like the go-kart chain? Like, can it not be attached to this?
Sorry.
I'm gonna find a drawing tool and I have a circle here.
Mm-hmm.
So what I'm saying is, does it have to be attached to this, or can it be attached to the bike chain?
It could be anywhere. It could be anything that's attached to the wheel, that's rotating with the wheel. So it could be, for example, attached here. As long as this whole thing rotates together, it could be anywhere in the structure, from here all the way to here.
You know how for the go-kart there will be like a chain going on like this?
Yep. Mm-hmm.
Yeah. So I'm going to change the color, get a yellow color. So can it be attached like here, so you can still detect how many times it touches the chain?
It would be tricky if you attach it to the because we'll see it in the next slide. What we need to do is we need to have a disk. Can you see this? This is not actually the cogwheel you're going to use with the chain. It's actually a specially made wheel for this sensor.
Oh, specially made.
Yeah.
I see.
So this wheel has to be attached somewhere in the. So what you can do is, if your motor is here, like this is the motor shaft, and this is the wheel, and this is the motor, like this. You could put that wheel here if you wanted to.
Oh yeah, that's good.
Right. So it doesn't have to be necessarily here. It could be anything that's rotating together with the wheel.
Just have to calibrate it then, wouldn't you?
Yeah, exactly.
Yeah.
So basically what we're going to do is we're going to measure the number of times the wheel rotates. Do you know how to convert the, do you know about the perimeter of a circle?
No, we haven't learned that yet.
Okay.
But I can look into it.
So basically, if you have a circle like this, okay, and if you start from here and you keep rotating this, okay, this way, and then it basically, when you rotate it, it comes to a certain point here, right?
Yeah.
At the end, so it'll come back one full circle, right?
Yeah.
Then it will have traveled a distance d, right?
Yeah.
Now this travel distance is basically a function of the radius of the wheel.
Yeah.
Because if you think about it, you take it from here and then open it up, it'll have a certain distance, right? And that's called the perimeter.
Oh, that's it. Yeah.
Right? And you basically you can calculate it by multiplying the radius by this number called 2 times pi. Did you know pi?
Yeah. Yeah.
Yeah. So this would tell you how much distance the wheel traveled from start to end when it rotated one revolution.
Yeah.
Okay. So if you know how many revolutions it rotates a minute, then you know how much distance it traveled in a minute, because you know the radius of the wheel.
Yeah.
So by using that, you can calculate how much distance it traveled, how many meters it traveled in 1 meter. And doing that, if you know the distance it travels in a meter, you can easily convert it to speed, right? Speed is how much meters does it travel in a second. So you divide it by 60, you get speed.
Oh, yeah.
Right?
Yeah.
So that's how you would work out the speed using a tachometer. In fancy maths, we can say the speed of the wheel is equal to angular speed times the radius. It comes from this exact same mathematics we learned. And the acceleration is equal to the angular acceleration times the radius. That also comes from the same explanation. Basically, if you had a wheel rotating one full circle, it travels the distance d, which is basically the radius of the wheel times the 2 pi, would give you the distance in meters. Okay.
Yeah. Yeah.
Now, there's also other methods to measure other than GPS or tachometers, but these are by far the most easiest and the most widely used methods. For example, if your motor controller might be able to tell you the speed. Some motor controllers do, especially if you're using something like a brushless motor. It has sensors inside to measure how many times it rotates, and from that you can work out the speed and so on. But it all depends on custom designs that you buy. Therefore, for this project, I would recommend using a tachometer. Cheap, easy, you understand how it works. So that's the best way to do it.
We can
Yeah.
get some of those for you guys if need be, if
Yeah.
you're interested. Yeah.
Yeah.
This would be helpful. Yeah.
In fact, I think we've got some, the ones we used last year.
Yeah. So now there are a number of different types of tachometers. So the one you see in this picture, you see this. Let me go. There's a wheel here, right? It's not a simple wheel. It's actually a special wheel. Each of these tooth you see is either a north pole or a south pole. Okay. So and this one here basically is a sensor that can identify whether it's a north pole or a south pole. So what happens is when the wheel rotates, it sees either a north pole or a south pole, and it keeps alternating. So you see a north, south, north, south, and so on, and it counts the number of these pulses.
Yeah.
Now this is what you have in your car. If you can open it up and see, you would see this exact same setup in your car to measure the speed in the actual car. But these tends to be expensive because you need to have this very specific magnetic wheel, a magnetic sensor. So it's not the best for something like what you are doing, because it costs a lot, and also it's a specialized part. What you could do is you could use something called the optical tachometer. Now, optical tachometer is very simple and very easy to understand. It simply has an LED on one side. So you have an LED on one side and a light detecting sensor on the other side. So the LED basically send a light beam, and on the other side there's a sensor that looks at it, picks it up, and say, oh, I got a light beam. And now what you do is if you cover this light beam using some blocking material like a dark disk or something, then there's no light. So we can do the same thing that magnet did, north, south, by putting a obstacle in the path of the light, blocking the light, or opening it up, and then blocking it, opening up, blocking it. And this can be done simply using a something called like a disk. Let me show you how we can do it. So you can 3D print or laser cut a disk that has many holes in it. Okay, and this is your optical sensor, optical tachometer, which has an LED and a light detector. When the hole aligns with the LED, it passes the light into the sensor. The sensor registered it as a light received. It tells the microcontroller Arduino Nano, I received the light, by giving it a high signal. When the wheel rotates, then it comes to this dark area where the light is blocked. And the photo detector realizes that it doesn't have any light. It goes back and tells the Arduino by sending a logic low signal saying that I don't have light. And as the wheel rotates, it creates this pulse that goes along.
That's
right?
pretty smart. Yeah.
We can count either the number of pulses. So we know when we are designing this disk, we know how many holes we put in, right? So if we say, for example, we had 10 holes in this, we count how long it took to get 10 pulses. And then we know exactly how long it took for the wheel to rotate one complete revolution. That's one way to do it. The other option is we can figure out what is the duration of this pulse. in the Arduino. And if we know the duration, if we know that we are going to get 10 pulses, then this times 10 pulses, and assuming that this is also the same distance, times 2 would also give us how long it took us to complete one complete revolution. So the whole idea about a tachometer is either counting the number of pulses or working out the distance of a pulse. For example, the duration it was high for, or logic 1 for, and from that predict how long did the wheel spend to complete one whole revolution. And if you know how long it took to complete one revolution, then you can work out the speed quite easily. Does it clarify how it works?
Yeah.
Right. So now moving forward, so assuming that we have n number of slots in this wheel that you would make, so this sensor, optical tachometer, you can easily buy. Les has quite a few of those that we used in previous years. You just buy it, and then what you do is you go to your manufacturing lab, you make a disc that has these holes. You can have 10 holes, you can have 5 holes, you can have 1 hole, depending on the number of, the more number of holes, you can work out things a bit more accurately. But for a cart that's traveling at speeds as what you would do in the race, it doesn't really matter. Even 1 hole is sufficient. Okay. So you work out, you cut this, and then basically you mount this on the axle or something. And this is where the motor, basically, let's assume this is the motor. And then this goes through the motor axis, and then this might be your wheel with the chain going around, and then you can figure out exactly how many rotations the motor is doing per minute or per second. And then you had to do some conversion, like Les said, because when this one does one revolution, your cart would have done, if you had a wheel that has a certain diameter, then it would have also done one revolution. Then you work out, okay, how many meters has it gone? And that would give you your speed of the cart, right?
Yeah.
Now, to have a look at it, let's basically use Proteus and work this out and see whether we can actually measure the speed. So what I have done is this motor itself that we are using to model your cart has a inbuilt tachometer that uses an LED. So it produces, basically at this point, it produces a series of pulses. In fact, it produces 10 pulses per one revolution. Okay. So every time it rotates around once, it produces 10 pulses. Now we are going to look at and figure out from these pulses the speed of this motor, or the cart in this case. And we're going to match it up with the speed that this one shows here. Okay. Now, just to explain this sort of visually, if you go to the simulation and run it, there is something called, do you know what an oscilloscope is?
I don't think you wouldn't come across that in year 12, I don't think, and especially if you haven't done the electricity part of it. Yeah.
I see. So basically, we are using a device that allow us to look at this waveform at this point, in this here. You don't need to know how it works. Just assume that you're looking into this point and you're seeing the pulses it generates in this window here. And you can see, like we discussed earlier, it creates these pulses up and down, and it creates 10 times every time this one completes one revolution. So we are going to basically, in our program, what we're going to do is to figure out speed. We're going to work out this duration here. And then we're going to assume this is the same duration. From that, if you know that how long is from here to here, we know how long it takes for 10 pulses. And if you know how long for 10 pulses, we know how long it took for this motor to do one complete revolution. And from that, we can work out the speed of the cart. So let's start writing the program to do this now. So let's close this program. And now let's open up Arduino. So in Arduino, what I have done is I have copied our program from last week, which basically had our serial set up. Then we had some calculations to calculate the voltage of the battery and some calculations to calculate the current coming from the battery. And then we printed the voltage and the current to the screen, so it shows us the voltage and the current. Now what I did was, last week we used some specific sensors here. I integrated those sensors into the motor. So this was part of the challenge from last week. Did anyone complete it? Levi, did you end up finishing it?
No, I've been, sorry, it's not really an excuse. I've been having an absolutely hectic couple of weeks at school.
I see.
So I haven't really, sorry.
Yeah. So basically what I did was I took the sensors from last week and I put it into together with the battery that's supplying a model of a motor that you would use. So if you run this just to sort of see how it works, you could see as the motor starts up, it draws a lot of current, and then it settles down at a small amount of current because now you have reached your steady state speed and you're traveling at a constant speed. So you can see this is updating the current, starts with a large current, the battery voltage is high, and then sort of carries on, and it matches with what we see here. So just showing that it works. And if you implement this for your design, you would have your voltage and the current coming from the battery, no problem. Right, now we are going to basically go and use the input from this tachometer. And first, what we are going to do is we are going to read how long this, so I'll draw this here. Yes, we said that we have a pulse like this. And we want to first work out how long is this pulse high for, okay? Let's say T here. So I'm going to write some Arduino code to do this now. So to do that, what I'm going to say is, I'm going to work out calculate the duration of the tachometer pulse is a high. So basically we are looking at how long is this time. Now to do that, Arduino provides you a really nice function. If you go to Arduino, I want to go to donate, I want to go to resources, and then references. If you have a look at this, there is a function called where is it? Pulse in. Right? If you look at that, it basically says it reads either a high or a low pin, and then it sends how many microseconds it's been high for or low for. Okay, so we are going to use this function here. So we are going to say I'm going to use something like a integer. Time high is equal to pulse in. Now then we need to tell which pin it is are we measuring and whether we want a high or a low. So which pin is this connected to here? It's connected to pin number 3. So we want to measure pin number 3. And we want to see how long is this pulse high for. Okay. And then I'm going to print this information to the screen so we can work out how long the pulse was high for. Time high in microseconds is equal to time high. Now if I verify this code, go to my Proteus file, go here, show it where my ELF file is, say okay. I'm going to run this. It should hopefully print how long this is, how long this duration is. So it's basically telling me that this time here is basically 18445 approximately. Let's say equal to 184.
Oh, sorry.
45 microsecond. Do you know what microsecond stands for? Any guesses on what?
Is it like 1 in 1,000 seconds?
That's milliseconds. So micro is even smaller.
1 in like 1 and 6 zeros?
1 in 6 zeros. Yeah. Yeah. So 1 to the power 10 to the power 6th of a second. Okay. So if you want to convert this to seconds, what do we have to do?
Not sure.
We had to divide it by
1,000?
2000s, right? Well, 6 zeros.
Yeah.
So it's going to be a decimal number now. So if we change this to float, and I'm going to divide this by 1, 2, 3, 1, 2, 3, right? I'll also have to multiply this by 1.0. Now if I verify this, close. Let's see whether it works now. So it's rounding it up to 0.02, close enough, right? If we divided this with 160 zeros, it'll be roughly 0.02 seconds. So it took 0.02 seconds. I should actually change the unit here to do one cycle, one pulse, right?
Yeah.
So how many seconds would it take to do all the 10 pulses?
It's like, is it like 160?
So this is the time it took to do one pulse. So time to do 10 pulses or one revolution.
Just times 10.
Times 10, yeah. Time revolution is equal to the time high times 10. Is it exactly 10 or is it 20? Because see, a pulse is going up and down, a high and a zero, right? We have 10 of these, but we only know the time from here to here.
Oh, so we times 2 again. So it's 20.
Yeah, it'll be 20. So it's 10 times 2. Right? So now we can say, instead of time high, we're going to say time per revolution in seconds, and then time revolution. Let's run this one. And now we run this. So it says now it takes about 0.38 seconds to do one complete revolution. Okay. Now,
Yeah.
a typical way motors are measured, how many revolutions it does, is by a thing called RPM. Do you know what RPM stands for?
Is it revs per second?
Revs per minute, RPM.
Oh yeah, per minute, yeah.
Yeah. So we want to calculate how many revolutions does it do per minute. How do we work this out? Plus,
so like
it
revs
takes
divided by
0.37 seconds. Sorry?
So it's like how many reps divided by seconds?
Yeah, so 60 minutes divided by time per each revolution, right?
Yeah.
So 60 seconds divided by, so let's say float RPM, okay, revolutions per minute, has to be equal to 60 seconds divided by time it took per revolution. Okay, and now I'm going to display RPM instead of that, and I'm going to say revolutions per minute, and the symbol is RPM. I'm going to verify this, run it again, and let's see what happens. So it's saying it's at 188 RPM, 157. Does it match with what we are seeing in the simulation?
So far, looks right.
Seems to be quite accurate, doesn't it?
Yeah.
So there you go. Now we know how many revolutions per minute the motor rotates in your cart. Now, if you had now the rest, the speed, calculating speed, it'll be different to every single cart, right? Because you have a different radius of the wheel, different mechanism, different number of pulses you're getting. So what you have to do is, based on your design, you follow these simple steps to work out how many RPM, or what's your RPM of the motor. Like, you know, in a normal car, it shows the RPM as well, right? Have you seen it?
Yeah.
On the dashboard. So you can show the RPM, and after that you use this RPM and the parameters of the slots, number of slots, the wheel radius, and all these things to work out the speed. Okay? Does it tell you how to do it? Now I'll show you another cool thing. So over here you can change the speed, right? Watch this window as I change the speed. So what this here is the accelerator of the car. So what I'm going to do is I'm going to hit the accelerator. It's going to speed up. Current ramps up to like almost 30-40 amps. Voltage drops because it's drawing quite a lot of current, and then RPM goes up to 442 now, right? Now if you go further, yep, hitting the acceleration as much as possible. It gives a lot of current now, and then current sort of settles down to about 36 amps, and the speed is now a maximum of 550 RPM. Okay. And now if you want to slow it down, let go of the accelerator. Current goes negative first. Why does the current go negative when you start braking?
It's feeding back into the battery.
Yeah. So it's called regenerative braking, and that's why some the electric vehicles are really efficient, because you don't, in a normal car, when you're braking, what you're doing is the friction in your brake system dissipate all that energy and waste it as heat. Whereas in an electric vehicle, what happens is all that current goes back into the battery, charging it. So you get back the energy rather than wasting it. So there you go. When you're at very low speed, the current is very small. It's running at very low RPM. Battery voltage has come back up to 24 volts. Any questions so far? So does this explain how to measure the speed?
Yeah.
Right. So the next thing we are going to do is, now that we know how to do speed, the next critical thing to measure is the temperature of your battery. So if you look at this, the battery is somewhere here. We want to measure the temperature of the battery here. The main reason is the batteries don't like getting too hot. If it's too hot, it's going to be quite dangerous. It might even work like a bomb. It might blast and creates issues. also the batteries don't like being too cold either. So you want to make sure that we measure the temperature of the battery, and then we report it to the driver. For example, if the battery is getting too hot, we ideally want some sort of an LED or a buzzer in the cart that will notify the driver saying, hey, the battery is getting too hot, something's wrong, you better get out of the cart before it blows up. So that's a very good thing to do. Now, to do that, there are many different ways to measure temperatures. But the easiest by far is to use something called a LM or a TMP36 or LM36 IC. It's a very small device with a case, black plastic case, and 3 legs. Now, 2 of the legs, one of the legs get connected to the ground, the other one get connected to 5 volts. The center leg tells you the temperature. Now, it tells you a number or a voltage that relates to the temperature. So every degree, it changes the voltage at the center leg by 0.01 of a volt. Now, that means at 0 degrees, that pin is at 0.05 volts, and every temperature rise above 0 degrees, every degree it goes up by 0.01 of a volt. So for example, if the temperature of the battery was 25 degrees, then you would read at the center leg of this device, the temperature sensor, 0.5 volts plus 0.25 volts, which is 0.75 volts. So we can easily work this out. We can take this, put it into the analog pin of an Arduino, and like we did with the voltage and the current, we can read this 0.75 volts, we subtract 0.5 of it, and then divide it by 0.01, we get our temperature, right? So that's exactly what we should do to work out the temperature. We connect the device up something like this. If you had the Arduino, you'd apply 5 volts and ground and take the center pin and put it into one of the analog pins. Now in this example, I have connected it to analog pin 3. Okay, so let's work out the temperature here now. Write a program to work out the temperature. So first thing is read the voltage at AD3 that represent coming from TMP36. Even before we do that, let's do a quick run. Let's run this simulation, the Proteus. And what I have done is I have connected up a voltmeter. So if I bring this volt temperature, you can click on these buttons to change the temperature. If I bring it down all the way to 0, I should read exactly 0.05 volts. Okay, exactly 0.05 volts. Now if I go up 1 degree, it'll be 0.51. 2 degrees, 0.52. 3 degrees, 0.53. 4 degrees, 0.54, and so on. You get the idea, right? So now we want to read this. So what we're going to use is, going back to here, we know that Arduino offers an analog read function to read these AD pins. So let's go to the analog read function. It basically asks which pin it needs to read, and then it reads that. We know it's pin 3 because it's connected to pin 3 here. So if you look at this over here, it's connected to pin 3 of the Arduino Nano. So we're going to read this into an integer voltage number or temperature voltage, temperature ADC. Remember, the analog read returns a number between 0 and 1023, right? Analog read, and we want to read pin number 3. Okay, and now I'm going to print this so we can see it. temperature ADC, number of counts. And this is going to be temperature ADC. I'm going to verify this and then now run this. Right, it's showing me 111 as the count coming from the analog to digital converter, which we learned last time. So, and if you look at the voltage, it shows as 0.54 volts at that point, which means it's 4 degrees because 0 degrees is 0.5 volts and every degree is 0.01 of a volt. Now, I'm going to close this so we can see a bit of things. Now, how do we know that 111 was the right number? Remember what we said was the analog to digital converter shows you 0 volts. If it's 0 volts, it shows you 0. If it's 5 volts, it shows you 1023. Now, what does 111 represent?
111, is that something that's very low voltage?
It is very low voltage, so we can work it out by saying 5 times 111 divided by 1023, right? Because 5 is represented by 1023. So 111 should be represented by 5 divided by 1023 times 11.
Yeah,
Okay?
I get it. Yeah.
So look at it. We get that voltage that we were seeing, right? 0.54 and a little bit of an error. So let's do that calculation. So we want to work out, now it's the floating number because it's a decimal number, float. Voltage ADC is equal to ADC, that's 111 times 5.0 divided by 1023. Okay, so now if you say voltage at ADC, and this is in volts, and I'm going to say change the variable and run this. Let's see what happens. So we got 0.54 volts, and if I keep changing this, for example, if I change it to 10 degrees, I know it should be 0.6 volts. Does it go to 0.6?
Yes.
Right,
Yes.
so how do we now convert this to a temperature? So how do we know 0.65? How do we relate the 0.65 to 15 degrees? What do we have to do?
Take away 0.5 and divide it by 0.01.
Exactly. So now we had to reverse what the temperature sensor did. So we had to subtract 0.05 and divide it by 0.01. So float, I'm going to create a new variable for temperature, is equal to what we had as the voltage at the ADC minus 0.05, because that's the offset that we had, and divide this by 0.01. Okay, now if we put that into, I'll call this variable temperature now, which is what we want finally, and it's in C, and this is temperature. Done. Okay, do you think it'll work?
Hope so.
There you go, 15 degrees. Now if I change this to, I don't know, let's say 50 degrees or something, 42 degrees, almost 42 degrees, right?
Yeah, almost.
And so on. There's a bit of an error because I remember we talked about this last time. When you're doing analog to digital conversion, there's always some error because it is a very not so much of a fine resolution like in a real analog signal. It's a digital signal. Right. Now That's all for today's lesson. So let's have a look at what we can do with what we learned. Okay. So going forward, this is your next challenge. What we want to do is we want to set up an alarm if the temperature goes above, for example, say 50 degrees. That's about the maximum you can do with the battery, lithium battery especially. We want to have a LED, a good, nice, bright LED, red LED on the dashboard that turns on, or a buzzer that beeps and tell the driver it's unsafe to be in the car. Okay, so that's one thing that you can do, and which you should also try to do. And also another thing that you can do is, the speed of the car, you can use the speed and work out the acceleration. So when you're doing, especially when you're getting prepared for your performance runs, it's good to work on your acceleration, because that's one thing that you can improve on in your vehicle. So you can measure the acceleration and figure it out, and then keep improving it as you go. Then the other thing you can work out is the total distance travel, which will be quite important when you're fine-tuning your card for your economy run. So if you work out the basically using the speed again, you can work out the distance it travels. Like we talked about, every time it goes, wheel rotates once, it travels 2 pi times r distance. So if you know number of revolutions it does, this times the number of revolutions tell you how much distance it traveled. So you can work out the distance your car's been.
Yeah.
So this would be the challenge for the coming week. Again, if you complete it, you can get an Arduino. Or even better, if we end up finishing the sensor board, we are building a board that has everything in it, so that you can basically take it and put it in your cart. If we have it ready, then we might send you one for free of that, one of those.
Yeah.
Okay. To give you some incentive to work on this.
I wonder what's the maximum degrees it can handle.
With this sensor?
Yeah.
From memory, I think it can go up to about 80 degrees.
Okay.
If I'm 80 or 100, it might be. We can have a look. So what you have to do is you search for TMP36, very popular sensor. There's something called a data sheet that has all the information about this sensor. It has a lot of numbers, so don't worry about it. So over here it says it goes from minus 40 degrees to 125 degrees.
Oh.
Yeah, so it works over a very large temperature range.
Yeah, that's pretty good.
Yeah.
Operation to 150 degrees.
Yeah, it seems like it can be operated at 150 degrees. But
wow.
It'll be accurate within this range.
Yeah.
So you can see if you go down in this big long document, there is a section. I don't know how to zoom this. Okay, here we go. You can see that is the sensor you are using, this one here. Okay.
Yeah.
Because that's that sensor, right? There are a number of different sensors. You can have a TMP 35, 36, 37. Each one has a different function. But you could see that at 0 degrees, it's 0.5 volts, right? That's why we use 0.5. At 50 degrees, it's 1 volt. At 100 degrees, it'll be, what is it?
Like 1.5.
1.5 volts, just roughly below like 1.5.
Yeah.
And that's also another contributing factor, that we didn't get exactly the right temperature when we kept increasing the temperature, because it's not exactly 0.1 volt per degree. There's a slight variation.
From this graph, looks like the TMP36 is the best one out of the three.
Yeah, it has the widest possible range. And it's very widely used because of that. Any other questions?
If it has wider range, do you think it's possible that like the TMP35 or 37 has like higher accuracy?
The 35 would have a higher accuracy, yes. because you're not in New Zealand, we're not going to go into negative temperatures, right? Especially not in the time when we have the race, because it's almost summer.
Yeah.
And we are definitely going to be in this range here. So this has much better sensitivity.
Yeah.
Like you said, correct. So if you had a TMP35, it'll be more accurate.
I see. Yeah.
Yeah.
Thank you.
Cool.
It's a question of how accurate we need to be, isn't it?
Yeah. We don't, I mean, if you're off by a couple of degrees, we're not too worried, because we would set the alarm for the battery at a conservative number. So you're not too fussed about whether you're reading 50 degrees or 48 degrees or 52 degrees, as long as you're conservative with your alarm trigger.
Yeah.
Levi, any questions?
No.
All right, so shall we then conclude today's lesson, Les?
Yeah, that'll be good.